Hello, my name is Siddesh, and today I'm going to demonstrate my proof of concept implementation of a smart car parking system using edge computing. This project is based on a two-tier fog computing model described in the paper, a low-cost two-tier fog computing testbed for streaming IoT-based applications. The aim is to show how placing computation closer to the IoT devices can reduce latency, save bandwidth, and still provide accurate real-time information to the cloud. The system consists of three parts. So first is the simulated parking sensors that generate occupancy updates for over 200 parking slots. Second is an edge node. It is implemented as a Flask application running over EC2, which receives the sensor data, processes it locally, and generates aggregated snapshots. The third and the final layer is the cloud layer. In this case, it is AWS S3 and CloudWatch, where the summarized data, performance metrics, and graphs are stored for long-term analysis and monitoring. The key difference from a cloud-only model is that only summarized data is sent to cloud, not every raw event. Now I'll show you the live demonstration of my project. I'll start the sensor simulation. As you can see here, that each parking slot is sending a small JSON packet to edge nodes containing the car parking ID, slot ID, timestamp, and the occupancy state. On the other side, we can see the edge node is receiving these events, updating its in-memory state and logging the number of events received. So for every 2 minutes, it creates a snapshot summarizing total slots, occupied slots, free slots, and occupancy ratios. So now we'll move towards the cloud. As we can see, we can stream the live data. So this is the live sensor data, the raw data, which the edge node is receiving. So when a snapshot is generated, the edge also updates a history file, regenerates the occupancy graph, and log performance metrics such as latency and data reduction ratio. So I'll show you the matrix. So this is the matrix CSV file. It shows us the important metrics such as raw events, raw bytes, the data reduction ratio, the latency, and the P95 latency, plus the occupied, free, and total slots. So these are the important metrics. So this is the car occupancy graph. This shows the change in free and occupied slots like over the time. You can see the occupied and the vacant slots. So this is the matrix overview graph. It shows the latency, raw event counts, and how little the data is actually being sent to the cloud. So the blue solid line represents the average latency, which is the time taken from when a sensor sends data until it's processed at the edge. As you can see, it stays very low, around 2 milliseconds, meaning the edge processes events almost instantly. The orange solid line shows the P95 latency, which tells us that 95% of all the events are processed faster than its value. It starts slightly higher due to initial warm-up, but quickly drops and stabilizes, showing consistent performance. The blue dashed line is the number of raw events per interval, which is received from the sensors. It stays constant because our simulation sends a fixed number of slots update every cycle. Finally, the orange dotted line is the percentage of data sent upwards to the cloud. It essentially at zero because instead of forwarding all the raw events, the edge only sends aggregated summaries. This is exactly what gives us 90% bandwidth savings compared to a cloud-only approach. Overall, this confirms that our edge layer delivers predictably low latency, processes a constant high volume of events, and drastically reduces the amount of data going to the cloud, aligning perfectly with the goal of a two-tier fog and edge computing model. In conclusion, this implementation validates the key claims of reference paper and demonstrates that a low-cost, easily deployable edge system can effectively reduce latency and bandwidth usage. In future work, I plan to extend this prototype to support multiple edge nodes, real wireless protocol, and more advanced cloud-based analytics for large-scale deployments. Thank you.